Hello. Today we're going to differentiate all of the trig functions. So that's great news. We've done exponential functions, we've done logs, and then we've gone back and integrated. So this time we're just going to do all the trig functions. Just a reminder, last lesson we did this proof that was for small angles, and we set the limit as x approaches 0 of sine x on x equals 1. Now look back for the proof if you haven't already, but that was there, and we could also just look at it graphically. When we sketched it on GeoGebra, we got something that looked like that, okay, and that's 1. So as it gets closer, that is the limit there. We're going to use that in our proof for deriving sine. Okay, so deriving sine. If I don't know how to derive something, I've got to go back to first principles. That's why it's called first principles. So let's look at sine x. The derivative of sine x using first principles is the limit as h, not x. H is that small bit, remember, I could use delta x. The limit as h approaches 0 of f of x plus h, which is sine x plus h, minus f of x, which is sine x, all divided by h. If I sub h as 0 in, I get 0 on the denominator, so I'm going to have to do some squidging. Okay, this is equal to the limit as h approaches 0. Compound angle, sine x plus h goes to sine x cos h plus cos x sine h minus sine x all on h. Okie dokie. This is equal to the limit as h approaches 0. I'm going to take this guy here and this guy here and factorize out that sine x. I'll zoom in a wee bit for you, okay? I'm going to factorize that sine x, and I get sine x outside of cos h minus 1. And then this other term just stays there. Cos x sine h. And we can split it actually. I'll do that on h plus that on h. Technically I should have that. Okay. Now what I'm going to do is just split those limits, because I can do that. That's one of the properties of limits. So I can say that's the limit as h approaches 0. Now I'm going to go, well, that's sine x times cos h minus 1 on h plus the limit as h approaches 0 of cos x sine h on h. Now h doesn't affect this. It doesn't affect sine x at all. It also doesn't affect cosine x, cos x. So what I'm going to do is take those through the limit. Sine x, limit, h approaches 0 of cos h minus 1 on h plus the limit, plus the limit plus cos x times the limit h approaches 0 of sine h on h. Look at this guy. Sine x on x, sine h on h goes to 0. That's 1. Yes. Sine x is there. what the heck is this guy? This guy is a little bit of a problem, isn't it? Because if I put h in, I get 0 on the bottom. So I'm just going to come over to the side here, and we're going to look at that one separately, okay? Limit h approaches 0 of cos h minus 1 on h. Now, I have to do something to it because I get 0 out. So what I'm going to do, and this is a bit tricky, is just go cos h plus 1 on cos h plus 1. Now, if I've just multiplied there by 1, okay, so it's all cool. That will become the limit as h approaches 0 of, I've got a difference of two squares there, factorized, so that's going to be cos squared h minus 1 on h cos h plus 1. This, well, sine squared plus cos squared is 1, so cos squared minus 1 is sine squared. Limit h approaches 0. These are really messy, aren't they? Anyway, sine squared h on h cos h plus 1. Yep. Now I'm going to rewrite this. Sine squared h is sine h times sine h. So I'm going to split this fraction, and I'm going to say, well, that's sine h on h times sine h on cos h plus 1. I can again bring that limit through. Limit h approaches 0 of sine h on h, because I can multiply limits. H goes to 0 of sine h on cos h plus 1. Now, this I know is 1. Again, he's popped up. This, I can just sub my h as 0 in. That's fine, because I don't get 0 on the bottom. That's the only thing. This one I will get sine of 0 is 0, cos of 0 is 1, plus 1 is 2, but 0 on 2 is 0. This thing now becomes 1 times 0 equals 0. So that whole big long thing was just so I could say that this guy here is 0. So going back equals sine x times 0 plus cos x times, what's this guy here? 1 equals cos x. Done. So I've now found the derivative of sine x is cos x. d by dx of sine x equals cos x. Now, you can do this just by looking at the graphs, and we'll do that afterwards, okay? I just wanted to run through the algebra of it. The derivative of sine x is cos x, but what about if I had y equals sine f of x? Sine of a function. Well, we can do this by the old substitution. If we let u equals f of x, that means du dx equals f dash x. I also know that y equals sine u, so dy du equals cos u. dy dx, and we've done this a million times, dy dx equals dy du times du dx. which equals dy du is this guy, cos u, I'm just going to sub that u back in, cos f of x times du dx, which is f dash x. F dash x. So if y equals, alright, if y equals sine f of x, dy dx equals f dash x cos f of x. Now an example could be, I'll just come over here, we'll do plenty of these examples later, okay? Sine of 2x plus 1, then y dash equals 2. Sine 2x plus 1. Okay, so now we're done with sine. We're going to move on to cos. To differentiate cos x, I'm going to use what we came up with here, and I'm also going to think about the relationship between sine and cos. I know that sine and cos are 90 degrees out of phase. D by dx of cos x equals the derivative of the same function, which is sine 90 minus x. Now I can just do that here. I can just do the derivative of that inside function. The derivative of that inside function is minus 1. The derivative of sine goes to cos. I know that cos, I can just change that back to sine. Minus 1 times sine x. So the derivative of cos x equals minus sine x. Now similarly, we won't go through it, but I could also say that the derivative d by dx of cos of a function of x equals the derivative of that function sine x, and it's a negative. And I don't think we have to do an example for that one. Looking at this, we can now just, so we've got this guy and we've got this guy up here. So I can see that if I differentiate sine, I get cos. If I differentiate cos, I get minus sine. If I differentiate minus sine, well then I get minus cos, because there'd be a minus 1 just hanging out the front. And then if I differentiate minus cos, I get minus sine, which is sine. So now we've got this nice circular pattern thing going on, which is lovely. Okay, thirdly, we've got sine, we've got cos, now we want tan. Everybody's favorite. Okay, so for tan x, the derivative of tan x equals, don't know yet, so what's tan? Tan is sine on cos, d by dx of sine x on cos x. What have I got here? I've got a quotient, or I've got a fraction, so I can use the quotient rule, where that's u and that's v, and y dash here, I won't do all the steps. It's v du minus u dv on v squared, and we'll just do that in our head here. V du, sine differentiated goes to cos, minus u, which is sine x, dv, the derivative of cos, is minus sine, all on v squared, which is cos squared x. Now cos cos x times cos x is cos squared x, minus times a minus is a plus, plus sine squared x divided by cos squared x. Cos squared x plus sine squared x is 1 on cos squared x equals 1 on cos is sec squared x. So now I've done all three trig functions. D by dx of sine x equals cos x. D by dx of cos x equals minus sine x. And d by dx of tan x equals sec squared x. These can also be used with functions in here where they spit out the derivative out the front. Now, that took a while. Apologies. Now let's do it the easy way. And the last one, here we've got sine x. I want the derivative. So what I do is I want the gradient function. I want the gradient of that line there. What is the gradient of that line there? Well, 2, it's going to be 1. Boom, got a gradient of 1. Now what I'm going to do, that's that point of 1. What happens if I move that point to here? The gradient there is going to be 0. So it's going to decrease, and then it's going to get to 0. That's the gradient. If I keep going, the gradient's going to turn negative, -1. If I keep going, and so on and so forth. I'll just press play on this so you can see the derivative of sine x is cos x. Nice, huh? So we could have saved a lot of time by doing that, but no. Now I'm going to change this to cos x. If it's cos x, the derivative here is 0. The derivative here is -1. So let's just bring that point. I'll let it play all the way through. It is cos x. Just keep an eye on the gradient. I'm going to slow that down. When we get to 0, the gradient here is 0. The gradient here is -1. The gradient here is 0. And then if I just look at that graph, I can see it's not sine, but it's negative sine. Okay. I can try it for tan. Do we know what sec squared looks like? I think we do, don't we? Well, let's find out. Tan. Try and just pause the video and think about what sec squared looks like. Okay. Y equals tan x. Alright, so there's our graph for sec squared x. Just try and think about why that is the graph for sec squared x. Okay. There we go, we've got it. We've got derived all the trig functions. Remember, functions can come out on the outside. Let's do some practice next time. Bye.